Hello everyone, I'm Norman Wildberger and welcome to Algebraic Calculus. In this video we're going to introduce an important family of curves that plays a critical role in the calculus. In fact, it's not much of an exaggeration to say that these curves are really the only ones that we can get control of exactly in terms of integration theory. Okay, and it's really quite a remarkable story because these curves and this development was really the consequence of the investigations of two French car engineers in the 1960s. So almost undoubtedly, this is the most important development in the theory of curves in modern times. And it's really remarkable that it was these two engineers who were responsible for this development. Okay, we're talking about Paul de Casteljau, who worked for Citroën, and Pierre Bezier, who worked for Renault. And in the 1960s, late 1950s, they were both interested in the question of how to specify curves in a nice way. It's very easy for us to draw a curve freehand on the page, but not at all so easy to specify a way of conveying the mathematical information of that curve efficiently to somebody else. And that's what they were able to do. They realized that certain kinds of curves could be described very efficiently by just a finite number of points called control points. And the simplest and most important examples are the quadratic de Casteljau Bezier curves and the cubic de Casteljau Bezier curves. So the quadratic situation, we have three control points, and these 3 points determine a quadratic curve, which turns out to be a parabola. Okay? And the curve goes through these two endpoints, doesn't go through the middle point, but the middle point specifies the tangent directions to the curve at these 2 points here. The cubic de Casteljau Bezier curve is a cubic curve with 4 control points. The curve goes through the endpoints, and again these two other control points determine the tangent directions of the curve at the two endpoints. Now these days in the literature, these curves are usually called Bézier curves, and I really want us to move from that to calling them de Casteljau Bezier curves, because Paul de Casteljau played just as much an important role in their discovery and development as did Pierre Bezier. So this is a remarkable achievement by two French car engineers, and we really need to acknowledge both of their contributions. So let's endeavor to call them de Casteljau Bezier curves from now on. If that's a little bit too long, sometimes I will abbreviate that by calling them DCB curves. Okay, so if we want to write it in a little bit shorter fashion. But these curves are going to be really important, and they really ought to play a prominent role in any calculus course these days. So in this video, we're going to introduce this rich topic. And it really starts with something that we've already talked about, with the idea of affine combinations of points. So let me remind you that if you have two affine points, P0 and P1, then the line joining them, which we usually denote P0, P1, just the product like that, that line can be described parametrically by adopting a vector kind of point of view. And the critical thing is to think about the vector v that joins P0, P1. So if P0 has coordinates A0, B0, and P1 has coordinates A1, B1, then the vector v from P0 to P1 is the difference A1 minus A0, comma B1 minus B0. That's the vector there. And so now, to specify points on the curve, we can proceed by starting with one point and then adding multiples of that vector to it. So for example, this point Q here, which I've drawn, which is about a third of the way from P0 to P1, can be described as P0 plus 1/3 V. We're taking 1/3 of V and adding it to P0. So there's the point P0, there's 1/3 of that vector, and if we add them, the A0 plus 1/3 of that will give us 2/3 of A0 plus 1/3 of A1. And the B0 plus 1/3 of this will give us 2/3 of B0 plus 1/3 of B1. So this is a very nice way of describing a point that's intermediate between B0 and B1. The coefficients, 2/3 and 1/3 here, are determined by the multiple of the vector v that we're choosing. And this kind of combination, where the two coefficients add up to 1, is called an affine linear combination. It's a linear combination where the coefficients sum to 1. And that's what we typically get when we're describing points on the line P0 to P1. So the general formulation is that a point Q lying on this line P0, P1 has the form 1 minus lambda P0 plus lambda P1. Lambda is then a parameter which, as it moves, we traverse the line. So for example, if lambda equals 0, then this coefficient is 1 and that coefficient is 0. We're just talking about P0. While if lambda is 1, then this one is 0 and that one is 1, so we're talking about P1. And for intermediate values of lambda, we're moving from lambda equals 0 up to lambda equals 1. So that'd be lambda equals 1/4, lambda equals 1/2, lambda equals 3/4, and so on. But we're not really restricted to values between 0 and 1. So for example, if lambda was minus 1/2, we'd be there. Lambda equals minus 1, we'd be there. Lambda equals 2, we'd be up there somewhere. But when lambda is restricted to the interval 0, 1, then we're describing the points that are traditionally between P0 and P1. That's the line segment, which we might specify like this, P0, P1 with a bar over it. And this particular kind of combination, when the coefficients are all between 0 and 1, is sometimes called a convex linear combination of P0 and P1, the convexity referring to the fact that we're between the 2 points. Okay, so now we're in a position to describe the simplest de Casteljau Bezier curves, the quadratic ones. So the quadratic DCB curve. So it starts with control points P0, P1, and P2. P0, P1, and P2. And it's created by, first of all, creating some auxiliary sort of secondary points, Q0 and Q1. Q0 lies on this segment and Q1 lies on this segment. And both of them are described in terms of a parameter lambda. Okay, so Q0 is 1 minus lambda P0 plus lambda P1. So it's exactly a convex combination of P0 and P1. Lambda equals 0, we're here, and lambda equals 1, we're here. So the Q0 is moving from here to here as lambda goes from 0 to 1. And exactly parallelly, Q1 is 1 minus lambda P1 plus lambda P2. So it's moving in a corresponding way from P1 to P2 as lambda goes from 0 to 1. So we have these 2 points. Q0 starts here and Q1 starts here. And as lambda increases, they're both moving. And when lambda equals 1, they both get to P1 and P2 respectively. This is an intermediate position. What we see here, this is Q0 perhaps when lambda is equal to, say, 1/3. And there's Q1 at that same lambda equals 1/3 position. Okay, so we have these Q0s and Q1s, which are somewhere on these line segments. And now we consider, say, another point, R0. R0 is a corresponding affine combination of Q0 and Q1 with the same parameter lambda. So it's 1 minus lambda Q0 plus lambda Q1. So the R0 is always on this segment joining the Q0 and Q1, and it moves from Q0 to Q1 in a corresponding way, just as the Q0 moves from here to here and the Q1 moves from here to here. So at this snapshot that we're seeing here, it's lambda equals 1/3, then R0 will be 1/3 of the way along. Okay, so that's what happens. The line segment Q0 sort of moves like this. And at every point on it, there's a point on that line segment that will then trace out this quadratic de Casteljau Bezier curve. And it turns out that this curve is always a parabola. It's always a parabola. And it's a parabola that passes through the point P0 and P2. That's not hard to check. When lambda equals 0, we're here. And when lambda equals 1, we're here. But furthermore, it's tangent at those points to the line P0, P1 and the line P1, P2. That's not entirely obvious, but we'll see that later. So let's have a look at things algebraically. So here are our expressions for Q0 and Q1 in terms of affine combinations of the points P0, P1 and P1, P2. And then here is the expression for R0, which is actually the point that's tracing out the curve. It's 1 minus lambda Q0 plus lambda Q1. So if we replace Q0 with this expression here and replace Q1 with this expression here, Then we get an expression involving lambdas, of course, and also the points p0, p1, and p2. And what are the various coefficients? The coefficient of p0 will be 1 minus lambda squared. The coefficient of p1, there will be a contribution here, lambda times 1 minus lambda, and another similar contribution here. So altogether, 2 times 1 minus lambda lambda. And the contribution of p2 will just be the lambda squared from here. So we're getting also an affine combination. So it's a combination of these 3 points, not vectors, but points, with coefficients that depend on lambda and have the property that they're always summing to 1. If you add this and this and this, you can see that basically the binomial theorem tells you that those things sum to 1. So these 3 polynomials that are appearing here, the nice little quadratic polynomials, we can give them some names. They're actually quite famous. They're called Bernstein polynomials. So they're Bernstein polynomials of degree 2. So b0, 2, so it's sort of the 0th Bernstein polynomial of degree 2. That's this one here. It's 1 minus alpha squared. I like to write my polynomials in terms of polynumber language, which we'll talk about shortly. And in that case, the variable is alpha rather than lambda or x or t or anything else. So in that language, the first Bernstein polynomial here is b0, 2. It's 1 minus alpha squared. Same thing here, but just an alpha instead of a lambda. And then the next one, b1, 2, is this one here, 2 times 1 minus alpha, alpha. And the third one, b2, 2, is just alpha squared. So these are the 3 Bernstein polynomials of degree 2. And we'll shortly see that there are Bernstein polynomials of any given degree. And they are very interesting, simple, but still pleasant polynomials that fit together in a nice way and have pleasant properties. And they're intimately connected with the geometry of these de Casteljau Bezier curves. Okay, so now let's move up one step to the cubic de Casteljau Bezier curves, where things get maybe a little bit more subtle and interesting. So now we have 4 control points on the diagram, p0, p1, p2, and p3. And we're going to do the same kind of thing that we've just done with the quadratic ones, but we're kind of going to go up one level. So the first thing that we do is we consider these intermediate points q0, q1, and q2, which are on these 3 arms formed by the 4 control points. And the formulas for them are now familiar. q0 is 1 minus lambda p0 plus lambda p1. q1 is 1 minus lambda p1 plus lambda p2. And q2 is 1 minus lambda p2 plus lambda p3. So as lambda goes from 0 to 1, q0 is going up this direction, q1 is going in this direction, and q2 is going in this direction. Okay, great. And now we're going to consider these 2 secondary points, r0 and r1. r0 is going to be between q0 and q1. It's the combination 1 minus lambda q0 plus lambda q1. So it's going between q0 and q1 with the parameter lambda. So q0 is moving, q1 is moving, this segment is moving, and the point r0 on that segment is also moving. But now there's another one like that. There's also r1, which is 1 minus lambda q1 plus lambda q2, moving on the segment between q1 and q2, correspondingly determined by the parameter lambda. Okay, so now we can go one step further and consider a point, say, S0, which is an affine combination of R0 and R1. Okay, so S0 will be 1 minus lambda R0 plus lambda R1. So all throughout, we're using the same parameter lambda variable. So you can just imagine lambda is like a parameter. You have a knob over here, a dial, and the lambda is then moving, and all of these things are moving depending on lambda. And what we're interested in is what the point S0 traces out. That's the actual cubic de Casteljau Bezier curve. And in this case, it'll look something like this. As lambda goes from 0 to 1, it will trace out something like this. Now it turns out to be a cubic curve, although it's not entirely obvious. And it has the properties that it passes through P0 and P3 when lambda is 0 and lambda equals 1. But it's also tangent at P0 to this segment P0, P1, and it's tangent at P3 to the segment P2, P3. So P2 and P1 and P2 are controlling the tangent directions at these endpoints. Now it's useful to observe that even though traditionally the curves are drawn with lambda typically between 0 and 1, in fact the formulas work for more general lambdas, in which case we get the natural extensions of the curve. So when lambda is negative, we'll get points like this, and when lambda is bigger than 1, we'll get points like this. And that's kind of pleasant. We can see more the cubic nature of the curve, perhaps something like this. Then it's an easy but interesting exercise to sort of unravel this and to express S0 as just a combination of the original 4 control points, P0, P1, P2, and P3. So I urge you to do that. And you'll recognize, I hope, that these are just the constituents that you would get when you expand a binomial expansion. In fact, it's what you get when you expand 1 minus lambda plus lambda cubed. Decreasing powers of 1 minus lambda, increasing powers of lambda, and some binomial coefficients, in this case 1, 3, 3, 1. So this thing traces out a cubic de Casteljau Bezier curve. Okay, so what are the natures of these de Casteljau Bezier curves? So we've said that the quadratic ones are in fact quadratic curves in the sense that they're conics and that the cubic ones are cubics, but let's actually kind of verify that in the case of the quadratic situation. So I'm going to explain to you using an example why quadratic de Casteljau Bezier curves are in fact conics. And I've said actually that they're actually parabolas, but first of all, how do we know that they're conics? So let's have a look. Here's an example. P0 is, say, 0, 0. P1 is 2, 3, and P2 is 5, minus 1. So an explicit example. And then here is the parametric form of the corresponding quadratic de Casteljau Bezier curve. 1 minus lambda squared times this 0, 0. 2 times 1 minus lambda, lambda times 2, 3, plus lambda squared, 5, minus 1. Now we can combine all of these things into a single expression. We just look at the various x and y coordinates there. We get 4 times 1 minus lambda, lambda from here. There's 0 contribution from the first term. And then 4 times this for the first term there, and another 5 lambda squared also contributing. And in terms of the second coordinate, we get a 6 times 1 minus lambda, lambda from here, and a minus lambda squared there. And then these things simplify to just 4 lambda plus lambda squared and 6 lambda minus 7 lambda squared. So this is a direct expression of the curve in terms of a parameter lambda. And we can see exactly how the x and the y coordinates depend on lambda. Well, we sort of lost at this stage the actual control points. So this is a polynomial parameterization. That's the really critical thing. That the expressions that are appearing here are polynomials in lambda. And in fact, they're quadratic polynomials. So this is a quadratic polynomial parameterization. And I want to now explain to you why it is that such a curve parameterized that way is actually a conic. So let's say we equate this to x and we equate this to y. So here are the x coordinates and the y coordinates in terms of the parameters. And what we would perhaps like to do is find the algebraic curve expression for this curve. In other words, we want to write down an equation just involving x and y without the parameter lambda. So that's really an elimination problem. It's a problem of eliminating the variable lambda from these two expressions. We have two expressions. There is an x, a y, and a lambda, and we want to get rid of the lambda. It's a very important type of problem. So how do we do it? We could take the expression 7x plus lambda. If we do that, then the lambda squared terms will cancel. So 7x plus y will be 7 times this plus this is 34 lambda. And then we can take this and solve for lambda. Lambda is then 7x plus y over 34. That's great. Now we can take this expression for lambda and substitute back either into this equation or into that equation, and we'll get something that doesn't involve lambdas, only involves x's and y's. So for example, if we substitute back into here, we get x equals 4, 7x plus y over 34, plus 7x plus y over 34 squared. And then when you sort of remove denominators and bring everything to one side, you can check that you get the algebraic curve 49x squared plus 14xy plus y squared minus 204x plus 136y equals 0. And that turns out to be a parabola, which is like this. It's not a parabola opening up vertically, it sort of has an axis like this. And if you substitute it into here, well, you end up getting the same equation. Now let me make a remark about this. So this is a conic, but it's actually a conic of a special kind. And it has to do with the nature of the quadratic coefficients. So associated to such a conic is a little 2 by 2 matrix, which captures the quadratic form, or the quadratic aspect of the expression. So I'm going to write that over here. So the 2 by 2 matrix that's captured here is the 49, that's corresponding to the x squared term, and then the 1 corresponding to the y squared term. And then this 14xy is expressed with a 7 here and a 7 here. You take half of them and put it on either side to make a symmetric matrix. So if you multiply this matrix by the vector xy on the left, row vector xy, and a column vector xy on the right, then that quadratic form would be exactly this expression here. And it's the nature of this 2 by 2 matrix that really determines the geometrical aspect of this conic. And in fact, the determinant here is 49 times 1 minus 7 times 7, that's 0. Okay, that's the critical thing, that this determinant is 0. That's actually the condition for having a parabola. Okay. So we'll see in the worked examples that this is not an isolated special case, but this is actually quite typical of these Casteljau Bezier curves, which are quadratic. All right, so we've illustrated a few important things here. The fact that the Casteljau Bezier curve can be expressed as a polynomial parametrized curve, actually with quadratic polynomials, and that we can, with some elimination, maybe a bit of ingenuity, get rid of the parameter to get an expression purely as an algebraic curve involving polynomial in x and y, and it turns out to be a conic, which is actually a parabola. So we've had a look at the quadratic Casteljau Bezier curves and the cubic Casteljau Bezier curves, and the general story for higher ones is very much like what we've already sort of outlined. But in fact, the quadratic ones and the cubic ones are the main workhorses for applications of this technology. And these curves are ubiquitous now in the modern world. A lot of graphics programs and design frameworks, are based all around these Casteljau Bezier curves. So, for example, fonts these days, fancy fonts. If you want to prescribe an A and a certain new type font, or whatever, it's typically done by having a breakup of the curve into little pieces, and each of those little pieces is controlled by some control points. So you have a finite number of points that really completely nail the nature of the fonts. But it's not just fonts, it's actually many aspects of modern design and computer graphics programs will involve these curves and this approach to curves. But from a sort of theoretical point of view, especially from a calculus point of view, there's some key facts that we have to at least be conscious of here, sort of the reason why they're important. And this is one of them, the following theorem, that a polynomially parametrized curve is a Casteljau Bezier curve, and conversely. In other words, if you have a curve which is given parametrically, okay, so you have an x expression which depends on lambda, and you have a y expression which depends on lambda, and if both of those expressions are polynomials in lambda, then that curve is actually a Casteljau Bezier curve. And conversely, if you have a Casteljau Bezier curve, then it's necessarily of this kind where the x and y coordinates are actually polynomials in the parameter. And the proof of this really reduces to the fact that the corresponding Bernstein polynomials of degree n, and here are the formulas for the n degree Bernstein polynomials. B0n is 1 minus alpha to the n, and then B1n is n choose 1, 1 minus alpha to the n minus 1 alpha. The kth one is n choose k, 1 minus alpha, n minus k times alpha to the k, and the nth one is just alpha to the n. So these are just the familiar constituents, really, of the binomial theorem apply to expanding 1 minus alpha plus alpha to the n. These are the Bernstein polynomials of degree n, and it turns out that they are a basis for the space of polynomials of degree less than or equal to n. So if we're looking at polynomials of degree less than or equal to n, they're linear combinations of 1, alpha, alpha squared, up to alpha to the n. This is called a basis for that space because every element in the space can be written as a linear combination of these things in a unique way. And it turns out that the Bernstein polynomials are an alternate basis for the same space. They have that same property that every polynomial of degree less than or equal to n can be written as a linear combination of these in exactly one way. So again, that's a linear algebraic notion, which figures very prominently here, and it's really the reason why these polynomially parametrized curves, the Casteljau Bezier curves, they're the same things. They're the same things. And that's perhaps one of the reasons why they're so important for calculus, because it turns out that the polynomial parametrized aspect of the curves makes it accessible to us in terms of finding definitions and computations of areas of these things, as we'll see. And a somewhat deeper fact about these curves is that a polynomially parametrized curve, in other words, something that's expressible this way in terms of a polynomial p of lambda, another polynomial q of lambda being the x and y coordinates, that this kind of thing is an algebraic curve. What does that mean? It means that there's a polynomial of two variables, say r of x and y, polynomial, such that r of p of lambda, q of lambda is 0 identically. So that these two polynomials together satisfy a third polynomial equation in two variables. So in particular, because we know that the Casteljau Bezier curves are polynomially parametrizable, it follows that the Casteljau Bezier curves are actually algebraic. But crucially, not all algebraic curves are the Casteljau Bezier. Okay, so this is, we're identifying an important subclass of the big family of algebraic curves. Here's all the algebraic curves, and over here are just the polynomially parametrized ones, the Casteljau Bezier curves. Okay? And those are the ones that we're going to see that we have complete control over when it comes to the integral calculus. The other ones, we really just do not have complete control over. It's a marked subdivision. Okay, so these are very fascinating curves, and we are going to meet them more, especially once we start having some familiarity with tangents. We'll be able to say some more interesting things about the Casteljau Bezier curves. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.